Hey everyone, how are you? Sorry about that, my computer froze. I had to reboot it. Okay, good. Is everyone able to hear me? Do we have audio? Yes, we do? Okay, good. We're going to continue from where we left off last time. So for that, I'm going to switch back to here. What? Oh no, don't tell me that's not connected again. Hello again. Now I have something. I don't know what happened. Okay. I'll figure this out soon. Oh no. Actually, that's not good. My video is not sending over there yet. Just a second. Yay. Okay, now we're good. Again, I have no idea what's going on. When I turned on my streaming computer right before class, it just was like super sluggish, which is not supposed to happen because it's running Linux and it's not allowed to. Anyway, let's continue. Yeah, I mean, the reason I use Linux for all my streaming stuff is because, you know, once it works, it works. And then the thing is, when you change it up for one thing, then it might need a while to go and fix again. But let me continue from where we left off last time. So the point of what we were doing was not clear to a lot of people, because it seems like, what have we done? We have tried to find a nice formula for the recursion for Fibonacci's, and it looks like all we did is get things that are more and more messy. Oh, it looks like I'm not the only Linux user here. Not true on all distros. That is true. But in this one, I tried to make sure I didn't do an update. Anyway, we're good. So I'm just going to make sure everything looks right. Everything looks right. Let's continue. Yeah. So where were we? We were like, okay, we got Fibonacci's. What are we going to do with Fibonacci's? We need to find a nice formula for it. And the idea was, I just want to do this quick review walking through what we had last time, because I want to just put the punchline on it and then continue. So if I look at this, we were like, okay, I have this Fibonacci thing, so I can set it up so that I have some kind of a matrix equation. So I have the Fibonacci n minus 1, and then I multiply by this matrix here. And that's exactly what it takes to go from one Fibonacci pair to the next Fibonacci pair. From that, we found out that you just want to take the power of this matrix. Yeah, so we just want to take the power of this matrix. And so the game becomes, what is this 1, 1, 1, 0 to the power n times something? To do that, we went and actually played with eigenvalues and eigenvectors without saying those words at all. Well, maybe I said them, but I don't require that you know what they mean. We were just noticing that if you had some way of writing a matrix as a matrix times some diagonal thing times its inverse, that's awesome. Because if you start to stack these together as you multiply, you get tons and tons of cancellation. Wait a second. Something just occurred to me. Is my board sticking off the screen? It so is sticking off the screen. We'll fix that. Yeah, because I was like, as I'm pointing, that doesn't look quite right. Now you're going to see weird stuff happen. No, that was the wrong weird stuff. That is me moving. I'm going to stay there. I want my board to move. Hi, board. Come on. Resize. Okay. I'm going to get this to work. Resize. Clearly, we have learned the phrase, if it ain't broke, don't fix it, which is what unfortunately I tried to do. Okay, now we're good again. So this is the board, and so what we had is that we found some way to go and write out this this power as multiplying things together and getting a bunch of cancellations. Then next thing that happened is we said, let's go and find out what are these interesting vectors that we can multiply by, where if you multiply by the vector, all you do is you rescale the vector. Okay. And equivalently, if I want to go and find out what vectors will do for this, the game becomes what numbers lambda will work for this to happen. And we found out that the lambdas that will work for this to happen are exactly the ones for which, if I try to solve this kind of an equation, where I have my matrix, I have these lambdas, when I try to solve this kind of equation, that there's like lots of solutions for the v's, in particular, not just v being 0 and 0. Because if I have v being 0 and 0, then of course when I multiply, I get 0 times, well, actually anything times 0, 0. And so that's not useful. And we'll see later on why the 0, 0 is bad anyway. Okay, as we continue, we're like, okay, how do I find that lambda? Well, I have this. And now in order to know when I have a non-0, 0 solution, that has to do with the determinant. And that's how we got this equation, which is the determinant of something equals 0 tells me the interesting lambdas. Okay, now I need to solve for those, and I have my very common equation that spits out the golden ratio as these choices of lambdas. So we found out that these two lambdas are really interesting, 1 plus root 5 over 2 and 1 minus root 5 over 2. from that, the next step was to say, now I know that there's going to be some way to find some non-zero numbers, a and b, so that 1 minus lambda 1, lambda 1 was the 1 plus root 5 over 2, and this 1 minus 1 and 1 and 1 and minus lambda 1, this thing actually multiplies to be just, sorry, if I multiply it by this, I get 0, and there's like a choice of non-zero things to do here. And if I pick apart, if I pull back out that lambda piece, then I find out that the original matrix, 1, 1, 1, 0, multiplied by this AB, happens to be a rescaled version by 1 plus root 5 over 2 of the AB. Okay, I can also do that and get a C and D. And the beauty of the whole thing, why we did all of this, is because then we now know that if I took my original matrix and multiply it by this AB and the CD as columns, then that turns out to be just the AB and CD as columns multiplied by the lambda matrix. That was what we did with the matrix multiplication. Okay, now we can multiply by the inverse of this matrix, P, if it exists. And the reason we know it exists was this stuff I commented towards the end of class, that, well, as long as I've gotten like these things not being just zeros, then the inverse exists as long as they're not like the same vector, meaning, no, not same, but like as long as they're not like parallel vectors. Okay, and they're not for the precise reason that the eigenvalues are different. Sorry, that the lambdas are different. Because the lambdas are different, I actually know that they can't be just rescalings of each other. And that brought us to the last thing, which I was chatting with some people after class, and they were like, it's not clear you've done anything, you've just made a big mess. And that's so far that is true. We have just found out that this 1, 1, 1, 0 thing is like all this like random nonsense, A's, B's, C's, and D's, whatever they are. It looks like a big pain in the pain to go and calculate them. And then that means that this fn plus 1, fn, is going to be just this thing. Figure out the A, B, C, D thing, invert that matrix, and ultimately multiply all this together, and you'll get a formula. Now, let's finish this off by being extremely lazy. So the way I'll do this is I'll say, let's continue. So if I want to continue, I'll say that this is equal to, well, I do know that the inverse exists. So since the inverse exists, well, let's continue writing this out like this. Well, I have a better idea. I won't copy things. I'll just write it underneath. You know this inverse? This exists. It's going to be 4 numbers. The 4 numbers, here are the 4 numbers. You see them? You can't read them. I just wrote them too small. But I'm going to say they're numbers. These are numbers. And I want to emphasize that I don't even care what the numbers are. They are legit numbers. They might have square root 5s in them. They probably don't have pi's in them, but they're just like some numbers, all right? And I'm going to multiply that by some numbers. Actually 1 and 0, but I'm calling them some numbers anyway. You know what happens when you multiply a 2 by 2 matrix of some numbers by that thing with some numbers? Well, you get a 2 by 1 thing which has some numbers. Okay. Now, so far, whenever I write a blob just means some legitimate number. Blob means some, I want to emphasize, some constant. Some constant. Oh, that needs to be more legible. Constant. And now, why would I call it a constant? I mean, what's a variable? Does anyone see anything in this expression that might be called a variable? I mean, constants are like, what is a? I don't know, something with square root 5s. What's lambda 1? That was 1 plus root 5 over 2. What's lambda 2? That's 1 minus root 5 over 2. Those are all constants. Can anyone see anything in this expression that might be considered not a constant? N. Yes, n. The only thing here that doesn't have like a fixed value. Because, it's fn. We don't care about just the Fibonacci number f 50 million. What about all the other ones, right? So n is the variable. So when I say some constant, I mean not involving n. And we're going to use that to our extreme advantage soon. Because 1 and 0, those are just constants, so they're blobs now. The inverse of this like 4-thing matrix, that's just some 4 blobs. I don't even care what they are. But now we're going to start to get a bit more sophisticated. What happens when you take this 2 by 2 matrix with lambda stuff and multiply it by these blobs? Well, I'm going to write it out this way. Do I have space? I'll go over here. So first, my A, C, B, and D thing, those are blobs. But now the way I'm going to multiply this piece, I have n, so I actually cannot write a blob. It wouldn't be correct for me to say that this lambda 1 to the n, 0, 0, lambda 2 to the n, multiplied by blob, blob, it is going to be a 2 tall and 1 across thing, but it's not blob, blob, because those blobs, those numbers depend on n. If n changes, they're not just like the same number, all right? So I need to take that into account. And the way I'll do that is I'll call it blob times lambda 1 to the n, and blob times lambda 2 to the power n. Okay, but now it's actually legit. This is actually correct. The reason is because whenever I wrote a blob, all that means is I had a big complicated number that's a legit number, but I'm just too lazy to write it down. Okay, and if I was to multiply it with some crazy number here, if you multiply this matrix by this vector, you'll get the crazy number times lambda 1 to the n plus 0 times the other crazy number. So that's just the crazy number times lambda 1 to the n. That's okay. And now let's finish this. If I have this, well, let me pause first. Does this blob arithmetic make sense to people? It might not be clear how we're going to use it yet. We're going to use it soon. But the important thing is I just know that wherever I wrote a blob, it is some number with square root 5s in it. And if I had the effort and time to work it out, I could write down what it was. But we're not going to do that yet. Or we're never going to do that. But now if I go and put this together, I then just have another way of expressing these, like some random number times lambda 1 to the whatever power. Now let's put these together. What's that? In blob language, can anyone tell me what the answer is? How would you multiply this? This is actually a 2 by 1 thing, but they're going to be maybe a bit long expressions. So I'm just going to emphasize. This is a giant bunch of space just because I'm going to write like big expressions in them. But this is really just 2 tall and 1 across. All right? How can I express what these things are after you multiply the blob, 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 blob by blob lambda 1 to the n, blob lambda 2 to the n? What kind of expressions go here? Can anyone help me with that? You can just raise hand and I'll just call on you. Typing is too hard. Thomas.
It would be like blob lambda 1 to the n plus blob lambda 2 to the n and both.
Yeah. So it's like a blob lambda 1 to the n plus a blob lambda 2 to the n. And the other one's another blob lambda 1 to the n plus another blob lambda 2 to the n. Okay. This just told me something really powerful. I now know something about Fn. Fn, by the way, is actually the bottom entry. Okay? So what I've just found out is, so Fn is equal to blob times lambda 1 to the n plus blob times lambda 2 to the n. Okay? Just to make things look a little bit more explicit, I can even tell you, actually that means that Fn is equal to blob times 1 plus root 5 over 2 to the n plus blob times 1 minus root 5 over 2 to the n. But this is interesting because I'm going to write an extra few words for all n. So now I know that the formula for the nth Fibonacci number is always equal to some like constant with like some random root 5s or whatever in it times 1 plus root 5 to the n plus some other constant which doesn't depend on n times 1 minus root 5 over 2 to the n. This is how I'm saving all the work of I don't care what any of those other blobs are in the middle. All I care about is what are the last 2 blobs, because that's in my formula. Does this make sense? I've proven something very powerful, actually. And usually if you read a textbook, they will not use blobs. They will just write like A's, B's, alphas, betas, run out of Greek letters or whatever. But what we've just found out is that there are just these 2 numbers that govern what is the Fibonacci number. What is the nth Fibonacci number? These 2 unknown numbers which we don't know yet. And they're like stuff with root 5s probably. Braden. Yes, we are not. That's why I was so lazy. We are just going to figure out what these last 2 blobs are because this is supposed to work for all the n's, right? So let's just choose 2 n's that I think are really easy, like f0 and f1. That's why I like f0. n equals 0 is a legitimate choice of n. So my point is these are two unknowns. Finally, the Greek letters will show up. I'll call the first one alpha and the second one beta, right? Because the point is I don't know what these two blobs are. As soon as I figure them out, I have a big formula for nth Fibonacci number. Okay, so let's continue. So what have we found out so far? What we found out is, so there are constants. Constants, I'm going to emphasize, independent of n. The constants are alpha and beta, so that for every n, I have that the nth Fibonacci number was equal to the first one, the alpha, times the 1 plus root 5 all over 2 to the power n, plus beta times 1 minus root 5 over 2 to the power n. All right? So now this is very powerful because I'm just going to go figure out two values of alpha and beta. I mean, I'll find out the values of alpha and beta, and then that's the end of the game. So what I can do is, because this is supposed to hold for every single value of n, let's choose two very convenient values of n. So definitely true for n equals 0 and n equals 1. So let's see what happens. For the n equals 0 case, not really case, but for the n equals 0, I get a statement. The statement is going to tell me a relationship between alpha and beta. This is one reason why I love to have my recursions start at 0. If anyone ever gives you a recursion of like a sub n or whatever, and it starts later than 0, just like arbitrarily back it up. You can always back it up. You can always be like, well, if I knew f whatever, I mean, I could make f negative 1 if I wanted to. You just figure out what number you'd stick there so that the recursion is still true to get the next one, all right? So we backtrack to f0. f0 is 0, okay? So 0 is equal to f0. And I really like taking things to the power 0. Nothing happens, right? The raised to the power 0 is just 1. And I'm just going to write alpha plus beta, okay? Because anything to the power 0 is 1. This is why I would rather do it with 0 and 1 rather than 1 and 2. 2 takes more work. Next thing, n equals 1. By the way, that's a true statement I've written so far. I know now that alpha and beta add to 0, whatever they are. Now, if n equals 1, f1 is 1. And now I have something slightly less nice. It's going to be alpha times 1 plus the square root of 5 all over 2 plus beta times 1 minus the square root of 5 divided by 2. But fortunately, the first equation gives me a good way to proceed by substitution. Okay, I think that the easiest way to solve this system is just to go by substitution. Beta is equal to negative alpha from the first guy. Now, if I know that beta is negative alpha, let's throw that into the second guy. So I now know that 1 is equal to alpha times 1 plus the square root of 5 over 2. And then beta is minus alpha, so it's minus alpha, 1 minus square root 5 over 2. Promise you this is worth it because the alpha is not bad. Actually, if I go and simplify this thing, I get 1 is equal to alpha times how much? Just root 5. Because I'm just subtracting. I'm just saying like 1 plus root 5 over 2 minus 1 minus root 5 over 2. The 1s cancel because it's like a plus and a plus, except there's a minus sign in between. And the root 5 minuses the minus root 5 to give you 2 root 5s, but it's over 2. Okay, this is actually very beautiful. I have found out that alpha is equal to 1 over root 5. And that means that beta is negative of that, which is negative 1 over root 5. And we have just found a formula for the nth Fibonacci number, which is the punchline of what we've just done here. Right, what's the formula? The formula is just 1 over root 5 times 1 plus root 5 over 2 to the power n minus 1 over root 5 times 1 minus root 5 all over 2 to the power n. And that's awesome. The first time I ever saw this formula, I was like, what? I didn't realize there was a formula for the nth Fibonacci number. I thought you always had to add them. But you just take some powers. All right, we're going to go on and do a lot more interesting stuff with this. But first I want to pause and say, let's go back a bit and see like why this was worth it, because this just made all of the work we did yesterday, 2 days ago, worthwhile. Because we just avoided all of the crazy arithmetic computation and replaced it with a very simple 2 equations and 2 unknowns that we didn't really have to do any work for. So I'm going to pull back a few pictures just to show like why was this so useful. So this is where we got to at the end of last lecture, which was where everyone was saying like we just got a big mess. Fn minus 1 and Fn, we got this giant mess of there were some numbers. If we actually worked out those numbers, we'd get some crazy stuff with root 5s in them. And I knew that all we'd have to do is multiply all this stuff together. And then the key was to note that, oh, there's one variable here, which is the n. And we could exploit that variable n to our advantage by just saying whenever I'm multiplying matrices or vectors, just keep blobs whenever it's going to be some like number that doesn't depend on n. And so those turned in, that inverse was fun. It's always fun to invert a matrix and just say it's just blobs. Inverting matrices is hard. It's computationally hard. But then you got this. And when you start multiplying everything together, the key thing is that whenever you saw an n, the n can't be subsumed into a blob because that will change with different values of n. And eventually what you end up getting is this amazing fact that the nth Fibonacci number is going to be some constant times the first lambda to the power plus some other constant times, well, possibly same constant, times the other lambda to the power. And then once I know that, the key is, oh, it worked for all n. So just pick 2 convenient n and figure it out. Are there any questions? This is actually a very important part of this particular unit. People won't be expected to know all the linear algebra, but this is like a very clear exam. It's done with like clear numbers, like how this works. Okay, good. And we're going to see some more versions of this very soon. So the next thing I want to do with this is I want to say, let's look at this formula. It turns out you can do an even better formula. Well, not even better, but it turns out that this formula can be simplified similarly to what we did with the derangements. Do you remember with the derangements, we found out some really, really neat fact that if you take n factorial and divide it by e, it gets closer and closer to a number, an integer, which doesn't deserve to be true? Well, here's something else that doesn't deserve to be true. It turns out that you can replace this purple box with round of something. What would that be? Does anyone see what I'm getting at? It looks like an arithmetic expression right now. I've got like some big multiplication minus some big, like some power minus some power. Thomas.
Well, the lambda 2, the 1 minus root 5 over 2 is like negative 0.6 or something. So as n gets really big, that's going to go to 0.
Ah, yes. So it turns out that this thing here, we're taking bigger and bigger powers of something that's absolute value less than 1. If I have anything which is absolute value less than 1 and I keep multiplying it by itself, sure, the sign flips, like the plus minus sign flips because it's a negative number in this case. However, as you keep multiplying it by itself, it gets smaller and smaller and smaller. Oh, so that starts to indicate that this first thing is probably going to tell you what is the nth Fibonacci number. Because if you think about it, imagine n was like 50. I'm too lazy to figure out what that is, but it's something to the power of 50, huge number. And you calculate the first thing, and you get some random number thing with some decimal points. But what will happen to the second thing if you raise to the power of 50? It's going to be practically negligible. You'll run out of digits on your calculator to write it down. Your calculator will come out at 0. Wolfram Alpha won't. It's pretty smart. But somehow, like over here, you're like adding or subtracting almost nothing. But it's very convenient. We happen to know that Fibonacci numbers are integers. Why? By induction. Because you started with 2 integers and you just keep adding stuff. So it's like still integers, right? So the point is, I know that the answer is an integer. And I know that this thing is like really, really small amount. So therefore, the nth Fibonacci number is just take this guy and round it to the nearest integer. I think that actually works. I just have to check that this extra adjustment amount is less than half. Let's go and check it out. Oh, I think I don't really need to check it out. It's obvious. The reason it's obvious is because I'm taking powers of something which is less than 1 in absolute value. So this part, like the power part, the absolute value, is already going to be less than 1. I think I do need to be careful. F0 might not be true. Yeah, F0 is not true. Because for F0, if I try to do this thing, my answer would be, if you try to calculate the first guy, what would you get? You'd get like 1 over root 5. Oh. Actually, that's true. It's true just because it works. F0 is 0. I mean, but with these, like with the really small n's, I'm worried because of the fact that as I raise powers, maybe something is going to, things to the power 0 are too small. But if I look at the second piece, what's going on in the second piece is raising to any power, even n equals 0, the inside of this bracket is always absolute value less than 1. So what that means is that the absolute value of this whole thing is always less than or equal to 1 over root 5. And that's great, because that's less than half. Root 5 is 2 point something. Okay? So what that means is if I was actually going to draw this thing on a number line, the way it looks on a number line is that you just have some number line. You'd actually legitimately have the fn somewhere. Fn is an integer. Right? And then what happens is you've got this other thing, this first part. Let's give it some kind of a, let's circle it in white. You'll have this white thing, whatever that is, but it's somewhere. I'm just going to put a dot for it. But then the gap between them is this green gap. And this green gap is less than half. And so that's exactly what it means to round to the nearest integer. Does that make sense? I'll have this thing, the blob I circled in white, and wherever it happens to be on the number line, there is an integer less than half away from it, and that integer just so happens to be fn. So what this has just showed you is that fn is also equal to round to the nearest integer of 1 over root 5 times 1 plus root 5 over 2 to the power n. I'll write for all n bigger equals 0. Because as I said, we could also think about f negative 1 if I wanted to. I could define that. But all of this analysis will break down if I'm allowed to stick a negative power in, negative number for n. Because suddenly if I have a number which is like minus 0.618 and you raise it to the power minus 10, actually, then that gets bad, right? Because the minus sign takes the reciprocal, and then suddenly it gets really, really huge. Okay, so this shows you that this Fibonacci actually is just with a round formula. Did that make sense? That's also cool. It's like, wow, who would have thought? These like funny coincidences that if I take 1 over root 5, multiply by a power of the golden ratio, you get closer and closer to an integer. Doesn't deserve to be true, but it is. Okay. So now we've just done this with the Fibonacci's. At this point, I actually want to go and play with one more matrix thing to go and show why that Cassini's identity was true. So this Cassini identity was the thing that we managed to prove with induction in an earlier class, where you go and find like 2 Fibonacci's which are spaced apart by 1, and multiply them together, and it turns out to be really close to the square of the one in between. Well, now this is interesting because it turns out that the form of this kind of a thing, f even plus 2, and f even plus 1 squared minus 1, let's go back to these matrices we have here. Well, these matrices we have here had some fn and some fn minus 1 stuff, right? And we know that it's true that if I take fn plus 1 and fn and multiply, it happens to be equal to this. I'm going to go back to the Cassini thing now. And on the Cassini identity, I'm going to just write down a matrix for fun. And the matrix happens to be fn plus 1, fn, no, it's a 2 by 2 matrix, fn under it, fn over there, and fn minus 1 over here. If I draw this up, and this is a 2 by 2 matrix, can anyone see any relationship between this 2 by 2 matrix and these kinds of things we're calculating? There's something you can do to 2 by 2 matrices that will give you an expression that is sort of like multiplying 2 f's which are spread apart by 2, and also doing something with 2 f's, like squaring and f in between. Andrew, what's the determinant of this matrix? Just for fun, okay? What is this? If I took the determinant of this matrix, okay, the way we always do this is you do the diagonal. I like to use not green. I don't like to use green and red on the same thing because some people are colorblind. And I once had a student who told me that. And from then on, I always made sure to use not green and red, but blue and red or pink or whatever. Right? The determinant is when you do this thing. You go down on the blue diagonal and then up on the pink diagonal. And this happens to just be equal to fn plus 1 times fn minus 1 and then minus fn squared. So can anyone give me another way to express this Cassini identity in terms of determinants? I just want to express it. Oh, Ising, were you raising your hand for the determinant or for the next thing? Uh-huh. 1 second. I don't want to take this call. But go on. Yeah. So this Cassini identity is exactly the same as the determinant of this particular matrix. I don't know if I drew it big enough. We'll see soon. Fn plus 1, Fn minus 1. And it's going to be equal to, you said it's either plus 1 or minus 1, okay? And when is it each of them? This is hard for me. I have to look for patterns. So when is it plus 1? Is it n is even or odd? What is it? Odd. Yeah, you're good. Okay, it is. Wait, is that right? Maybe? I'm not sure. So okay, here's how I always do it. Give me an example. 7. 7 is my example. Okay? So it's just like, what would I do? No, I mean, this is seriously what I do. So if it was 7, it would be like determinant of F8, F7, F7, F6. Okay? That's equal to F8, F6 minus F7 squared. And now I can see what I want. Right? Like what I want is, it comes from this guy, I think. These are even things, so it's minus 1. Oh, I think you're right. Wait, no, are you right? I'm slow at this. I think the minus 1 is if it's odd. And the plus 1 is if it's even. I'm not sure if that's what you said or not, but it doesn't matter. We figured it out now. If n is odd. Okay? So I think this is right. Yeah, it worked for 7. Okay, so this is right. And then the question is then, is there another way I could write this? Like plus 1 if n is even, minus 1 if n is odd. That's like a lot of English. But it turns out there's another way you can write this whole thing. What's an expression that is plus 1 when n is even and, Christopher?
Just -1 to the power n.
Okay. Now, do we have any hope of trying to prove that the determinant of this funny thing is -1 to the power n? That would be great. Well, this thing that we have written, fn plus 1, fn minus 1, is interesting because you can draw that. So if I drew this thing going up and down, what does that accomplish? Well, I'm just saying it's sort of like 2 columns, and each of those columns we've seen before. Okay. Here's what I'm going to do with those. And I'm realizing I should probably have shifted my indices by 1 more, but we'll be able to play with this. Let's go back here. So I know that this fn plus 1 fn thing, that's equal to, take this matrix, raised to the power n, times f1, f0. I'm actually going to shift it forward by another one, and you'll see why. What would happen if I just felt like making fn plus 2, fn plus 1? Okay, and let's suppose I actually want to keep the same 1110 to the power n. What would I need to multiply by instead? It's not going to be f1, f0. And I actually wrote this like offset on purpose. So this is like a, what are we doing anyway when we multiply by 1, 1, 1, 0 to the power n? That does some kind of like shifting of the f's. Subhashish.
Multiply by 1, 1.
Good. 1, 1, you mean f2, f1.
Yes.
Is that okay? So all I'm saying here is that if I have this fn plus 2, fn plus 1, well, if I did this like multiply by this 1, 1, 1, 0, I kind of advance my vector along by n steps. And so if I had f2, f1, after n steps it would be f2 plus n and f1 plus n. Why did I do that? Well, I did that because now I know what it looks like if I were to make a matrix which has fn plus 2, fn plus 1, fn plus 1, fn. If I made that matrix, can anyone help me out? How does that end up looking? And here what I'm emphasizing is we kind of got like the same 1, 1, 1, 0 to the n times like different vectors. Venkatesh.
Would it be 1, 1, 1, 0 to the n times a 2 by 2 matrix that's f2, f1, and then f1, f0?
Yeah. Let me use colors on the inside just to emphasize how I could pull that off so easily. The f2, f1, that was the pinkish purple stuff. f2, f1, and then the white stuff gave you f1, f0. And this is the thing we talked about last time, where it's like if I have a matrix, square matrix, multiplied by some kind of a column, then if I took the same square matrix and multiplied it by like 2 different columns, which are just made as different columns, the output is you just compute each matrix times one of the columns and slap it there. Is that sort of ringing a bell from last time? Like this was how it comes from like multiplying of matrices. And if you want to have a quick review of why that is the case, it's because, remember, this 1, 1, 1, 0 to the power n, that's just some blah, 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 blah. It's a 2 by 2 thing. And if I have a 2 by 2 matrix over here, and I multiply, and I want to know what should I put in like the first entry there, the way you do it is you go and grab this first column, and you hit it against the blob blob stuff. Notice you don't even use the white numbers at all. So that's why you'd expect that the answer you get is the same as if you just had, that thing there multiplied by that purple pinkish column. You don't even use the white column. And if you want to know what ends up going in the bottom left piece, what goes in the bottom left piece is, again, you just use this like leftmost column, multiply it by your blobby nth power thing, and that will give you the same answer as if you grabbed that pinkish purple column and multiplied it by this part of the nth power. Okay? This is actually pretty cool. Does anyone know what is f2, f1, f1, f0? This is like not fair. It shouldn't be. But something like very unusual happens. This is just like this is actually legitimately a pure coincidence. But something unusual happens here. Sam. Oh, Sean. I can't read.
It's 1, 1, 1, 0.
Oh, it's another 1, 1, 1, 0. How nice. So the answer is actually just 1, 1, 1, 0 to the power n plus 1. Now, why is this exciting? We cared about determining or taking the determinant of this like other matrix. We wanted like fn plus 1 or something. But why is this interesting? This is where we are about to use like a certain fact about determinants. Braden.
Well, if we get the determinant of the left-hand matrix, we know it's going to be the same as the determinant of 1, 1, 1, 0. Oh, that to the power of n plus 1.
You just used an important fact, okay? You used a fact which is that the determinant of the product of two matrices, yeah? Is that what you mean? Yep, determinant of product of two square matrices, AB, is equal to determinant, I'm just going to write like this, determinant A, determinant B. There we go. this is a fact of determinants. I won't be able to prove it here just because at this stage we're giving the entire linear algebra class in approximately like 3 lectures. But I will say the reason why, this thing is the heart of why multivariable calculus works. If you use these Jacobians and like change of variables, this is part of the chain rule. But in any case, determinants of matrices multiplying together is the product of the determinants. Don't try to do this with sums. It's not true with adding. It's only true with multiplying. Okay, but then over here, it's like, well, then I just need to take the determinant of like 1110 times the determinant of 1110, multiply it and multiply it and multiply it. You know, because if I'm raising it to the power, if a determinant of the thing raised to the power n plus 1, you can use this like breaking apart determinants many times to just find out that the determinant of this left thing is just the nth power, n plus first power of the determinant of the right thing. Was that step okay and not too fast? It's like, because the determinant breaks like multiplying. Okay? So what we just found out is that was supposed to be an arrow. Here we go. So the determinant of fn plus 2, fn plus 1, fn plus 1, fn is equal to, you just take the determinant of 1110 raised to the power n. And if you want to see that a bit more slowly, the easiest way to do that is, it's like if I had n equals, there's a typo. It's not n. It's n plus 1. If you want to see that a bit more slowly, it's like if I want the determinant of a matrix times itself. Oh yeah, that's the determinant of the matrix times the determinant of the matrix, so it's the power 2. What if it's the determinant of the matrix to the power 3? Well, then that's like determinant of the a squared times the determinant of the a. Oh, but the determinant of a squared is determinant of a times determinant of a, and then times determinant of a. So that's how it breaks apart. What's the determinant of 1110? Ah. Oh, Isain, are you raising your hand?
Yeah, I think it's going to be minus 1, but then we're going to be multiplied by a bunch of like minus 1 will be kind of like of the value of n equals to 1.
Yes, that's it. The whole thing just fell out. Okay, so somehow it's like on the one that I wrote on the previous screen, we had n's and we had like n plus 1, n minus 1. Here I have n plus 2, n plus 1, n plus 1, n. But it doesn't matter. The only thing that matters is the power of the power of minus 1 is like the diagonal thing, those diagonal things. And I'm going to temporarily flip to the previous screen. The previous screen, what we wanted was minus 1 to the power n, and the n there was the stuff on that diagonal. Okay? So we actually got what we wanted. It's just like the indices shifted off by 1, but that wasn't what we cared about anyway. What we cared about is that if you're ever going to multiply together two Fibonaccis, which are like something and then 2 later, well, that's going to be the same as multiplying, like squaring the Fibonacci in between, and either a plus or a minus 1, and this tells you which one. So this is actually not fair. There's no reason why you should be able to do it this way, but this is the niftiest proof I've seen of this Cassini identity, and it ties into what we've just done with noticing that Fibonacci's happen to have something to do with multiplying like a power of a matrix by a vector. Okay, so I want to say this is the key part I wanted to get to today to make sure everything can sink in and digest. What we have just seen just basically involves trying to find a way to make this form, right? I always want to spend some time thinking like, why in the world did we do all this? I want to say that the gold came from this form. The gold came from the form matrix times diagonal times the inverse of the matrix, just so that I could write diagonal to the power n. Like if you think about why I needed everything to be the way it was, I needed to have the blob arithmetic work out. I'm skipping forward. The blob arithmetic entirely relied on the fact that I have something to the power n. So then the game became, how could I possibly get that blob arithmetic? And the way to get that blob arithmetic, if you go back here, was then I need to find some way that I could possibly find a diagonal matrix. And the beauty from the linear algebra was that that kind of a diagonal matrix happens to come if you're able to find some numbers lambda, so that if you take the original matrix times a vector, you just get the lambda rescaling that vector. This is why at some point when you learn a matrix class, or now if you're reviewing one, that's why that entire notion of this eigenvalues and eigenvectors is so valuable, because that's just about figuring out when, if you multiply your matrix by a particular vector, it's just a rescale. Okay, are there any questions? So this is the heart of this piece. Okay, I wanted to add another comment, because now we actually have a few minutes. I want to say something about exam strategy and also about curves and mid-semester grades and all of this. I actually do realize that the exam was too hard, and so I will be doing my best to go and make the rest of the exams not as hard. But at the same time, I want to give a little bit of a tip on the exam strategy, because I was talking to a lot of students at office hours or at other points, and I realized that I probably should have told everyone ahead of time that the exam wasn't designed for people to solve all 5. I was actually kind of surprised if anyone did. And at the same time, it turns out that a lot of other exams people are used to. You're used to being able to solve all of them, at which point you sort of budget your time across all 5 questions. I wanted to say, usually the way I make these, the question 5 is usually designed to be look, if you really get everything super fast, then you can go and try to fight with that. But that's not anywhere close to the difficulty level of the other questions. So it's actually better exam strategy in the future to be first of all, the curve is going to be pretty generous. Even if question 5 doesn't exist, you'll be okay. But it's actually much wiser to put your energy on questions 1, 2, and 3 than to put the energy on the 5. So I just wanted to give that as the general advice. And the reason I do that is because it just so happens that in these classes that I teach, I know that there's a wide variety of backgrounds. And so I didn't really want to make something where the difference in score between somebody who, I guess, has already seen a lot of stuff before and somebody who's new is a lot of points. Actually, by putting a virtually impossible problem for question 5, it actually compresses the curve. So if that sort of makes sense. Because the point is yes, if you were so fast that you could do the whole exam in half the time, great, now you actually can try to do question 5 and you might get 10 more points. And that way, it's the curve of the difficulty is kind of exponential. On this, I also realized it's in some sense because I do teach the Putnam class. So I think I was like, this is a reasonable exam, because some of you know that the Putnam exam is an exam which every year has 120 points, and the median score is 1 point out of 120. So I'm sort of used to that kind of an environment. And so I wanted everyone to know the way these are always going to be designed. The last question is going to be very hard on purpose. The 4th question is already going to be quite a stretch, but in general, if you focus your energy on 1, 2, 3, they're all designed so that you shouldn't be able to just see how to do it based on something we've done before. But if you just sit on it for a while, you'll probably find a way to crack it open. So I just wanted to give that general advice. And if people have other comments, please feel free to chat with me separately too. I do want to make this class more reasonable. Yeah, and I know that there were a lot of people who actually didn't realize the calibration and made a mistake of maybe not allocating time. But don't worry, I'm going to try to make sure this works well. So, all right, I'll see you guys all on Monday. Take care.